my pleasure to welcome you to this disputation. My name is Juliette Soulard. I'm associate professor at the Department of Electric Power Energy System, and I'm going to chair this session. Before I forget, make sure that all these electronic devices are switched off so that it doesn't disturb the session. First, I will introduce the important people for this activity this afternoon. The respondent, Vedran Peric, and the examiner, Professor Mani Venkata Subramanian from Washington State University, USA. Welcome. The examination committee is containing 5 people. Professor Hans Pettany from KTH, who is also the chairman of the committee. Professor Luis Rucco from Comillas Pontifical University in Spain. Professor Marian Popov from Delft University in Netherlands. Professor Kjetil Ulen from Norwegian University of Science and Technology in Norway. Welcome. And Professor Matt Bolen from Luleå University of Technology in Sweden. The research that is going to be presented this afternoon was carried out at KTH, started in September 2011, under the supervision of Luigi van Pretty. For the first 3 years, the research was funded by SET's Erasmus Mundus program, and as part of the program, Vedran spent 9 months at TU Delft under the supervision of Xavier Bombois. Since September 2014, the research was continued as part of a European project in the MP7 plan called iTesla project, and Christian Royas from KTH joined the supervision team. It's also stated here that the work presented in the thesis has only been carried out by the supervisors and the respondents, and that no third parties were involved. The session will go as follows. First, Vedran will present his work for 45 minutes or so. Then the examiner will have a discussion with the respondents, and then it will be the turn of the evaluation committee to ask questions if they want to. And then after that, the public will also be given the occasion to ask questions to the respondents. But then I have my first question for you, Vedran. Do you have any comments of any formal defects in the thesis you want to?
Not really defects. Maybe I would like to add. Thesis is written as a monography, but it's mainly each chapter is based on a publication that was published, or a journal, or a conference paper. So I try to, of course, to make it as a monography, to have a flow and everything, but also you can full story you can find also in these publications that you can find at the end of the thesis. Not publications, but at least references. Mm-hmm. That's all.
Okay, thank you. But then the floor is yours for your presentation.
Okay. Thank you very much, Juliette, for the introduction. And thank you very much all for joining. It's really great to see you in this number. And of course, I would like to thank all the committee members and the opponent for their time and the time they spent reviewing the thesis. So, the main question behind this thesis is how to estimate properties of oscillations in electric power system using real-time measurements. And not just that, we want to do this mode estimation in a non-intrusive way, which means by doing this estimation, we don't want to disturb or jeopardize stability of the system by any means and at any moment. And I will try, this is the main question that I will try to address in several steps. First, I will talk about oscillations and why we use modes to describe these oscillations. And I will talk about basic principles of mode estimation, and then I will talk more about my work and scientific contribution of this thesis, which is of course the most important part. This includes optimal probing signal design, optimal signal selection for mode estimation, as well as what to do in case of non-vital loads, which has some negative effects on mode estimation. And then I will finish with a prototype. I will present you a prototype application that I developed that can be quite easily deployed in real control centers. And of course, I will finish with conclusions. So I structured this thesis also to introduce this topic to a more general public, but of course also to talk about specific contributions. So let's get started. So oscillations are very general term, and oscillations can be associated to any dynamical system. And dynamical system can be pretty much anything. For example, plane, car, train, even this building is a dynamical system. And in order a dynamical system to oscillate, it has to be disturbed by some excitation, some disturbance. And in case, there are different types of these disturbances, but in case of this building, for example, any kind of traffic nearby, or even when wind blows, or just people walking around, it will cause some small disturbance on the system. And due to this disturbance, the building will oscillate. Even now, this building oscillates a bit. Of course, we don't feel it, but it is possible to measure it. That's something what civil engineers do. And this kind of excitation we call ambient, because it's coming from the ambient, from the surrounding. And we are not really able to isolate our system from these disturbances. And what's more important, these disturbances are always present in the system. So that's one type of disturbances. Another type of disturbances are caused by some events, and we usually call these disturbances large disturbances. For example, in case of earthquake, or here at KTH, in the recent months, you have witnessed these drilling and dynamite explosions. And that's something when sometimes we really feel these vibrations. And what's interesting about oscillations, all systems tend to oscillate at some particular frequencies. And these frequencies are called modes of oscillation. And there are two parameters that describe these oscillations. First one is, of course, frequency, which describes how fast this vibration occurs, and damping, which is a measure how severe this oscillation is, or for how long this oscillation will last if we don't have any further excitation in the system. And we can analyze these two parameters, of course, by using mathematical models. And these parameters correspond to eigenvalues of the linearized model of the dynamical system. And these parameters can be computed. So up to now, I haven't mentioned power systems, but power systems are just another dynamical system. And all these concepts can be applied to a power system. We also have this ambient excitation. But in case of power system, this ambient excitation is due to random load changes. Whenever you plug in some device in the electric outlet, you cause a really small disturbance in the system. And if you analyze how people behave in some short period of time, all these changes are completely uncorrelated and they are independent, which means that our dynamical system is excited by white noise. So that's the ambient excitation in power system, but what actually oscillates in power system? Well, you know that vast majority of electricity in present-day power systems is produced by synchronous generators. And synchronous generators have rotating masses, rotors, and what's interesting that all these rotors rotate at the same speed. Even though these generators can be really far away from each other, like thousands of kilometers, they all rotate at the same speed. This is possible because all these generators are connected by the transmission grid, which in this case behaves just like a shaft that connects all these rotating masses. And of course, like any other mechanical shaft, this electric shaft is also elastic a bit, which means that at some particular point of time, there can be a difference in speed between these rotors. For example, in this, if you have this first rotor that rotates at some speed, some particular point of time, this one can rotate a bit faster than the second one. And what happens in this case is that, of course, after some delay, the second one will try to follow the first one. And in that moment, kinetic energy from the first one is transferred to the second one, which means that the first one is losing kinetic energy and is slowing down, while the second one is receiving kinetic energy and speeding up. And after some time, we'll actually have opposite situation. The second one will be faster than the first one. And the same thing will happen in the opposite direction. And that constitutes these oscillations. Energy is oscillating between rotors. And these oscillations are real. That is something that we can measure in any variable, or almost any variable in the system, such as voltages, currents, power. And here you can see one event that happened several years ago in Europe. So these oscillations are real, but why do we care? First thing is that if you are in a building that vibrates all the time, a lot, then probably you wouldn't like to be in that building, because after some time it can collapse. And the same thing can happen in power system. And we call that blackouts. Of course, it's not that we have anything against blackouts, it's just they cost enormous amount of money. There was one famous blackout in 2003 in the eastern part of the US, and the cost associated to that blackout was measured in billions of dollars, $5 to $10 billion. So it really makes sense to spend a few bucks on the research and maybe finance PhD students like myself, and maybe help in preventing these catastrophic events. But luckily in Europe, we haven't had such events. But even if we didn't have that, there are still negative effects of these oscillations. First, they occupy transmission capacities. They increase losses. And there is also wear and tear associated to the equipment because of these oscillations. I like to imagine these transmission capacities as electric power highways, which means they are extremely expensive. And if you have built them and spent a lot of money to build them, you definitely don't want to use them just to carry some useless traffic on them. So that's, of course, very expensive. So we are really motivated to suppress these oscillations. And first thing what we do is that we need to monitor these two critical parameters that I mentioned before, frequency and damping. So that's the first thing that we have to do. So overall, this is what we want to do. Our main objective is, of course, to avoid blackouts. We do it by real-time monitoring, and for that we use synchrophasor technology. I will talk about that a bit later. And with these measured signals, we want to design decision support tool that will help operators to make some corrective actions, or we want to initiate automatic control actions. So that's the overall idea what we want to do. But how we estimate these modes? Well, for that, we need some mathematical model of the system. So here it is. Because we're dealing with this ambient excitation, we assume that we don't have large disturbances in the system, which means that we can use a linear model to describe the system behavior. Of course, it's a strong assumption, but that's something that is widely used. So I use it as well here. Excitation to this linear model is, as I said, can be described by a white noise process. And of course, outputs are our measured signal that we measured by PMUs, phasor measurement units. And if we analyze one particular signal, it can be shown that all these loads can be aggregated and represented by a single aggregated load that is represented by a white noise. And in that case, we have only single input, single output system. And what's nice about this simplified system that these modes that describe oscillations are the same in this small one as in the original one. So all that we need to do is to identify this system or this transfer function. Another thing that we can do to improve this oscillation is not just to rely on ambient excitation. We can also excite our system potentially in a really controlled manner. So in addition to this omnipresent ambient excitation, we can create additional controlled disturbance. And in power system, we call that probing. And this probing can be generated using FAC devices, automatic voltage regulator, turbine governance, and equipment like that. But of course, in this case, our measured signal will change a bit because we have additional component that comes as the result of this probing. And now our system looks like this. It has these two transfer functions, G and H, that we want to estimate. There are actually many methods how to do this mode estimation, and the introduction part of the thesis, you can find, I think, quite comprehensive survey of all the methods. But underlying idea is that we want to find the model that will match measured output. So we have our measured signal, and we have output of the model, and we want to minimize the difference between these two signals. So that's an optimization problem, and the solution is, of course, the identified model. And first, before we run this optimization, we have to decide on the model structure of the model. So here, you see quite general form of the model with two transfer functions. And if A and D are equal, that model structure is called Armax. Otherwise, this is Bog-Jenkins. And these two model structures are widely used. And what's important, these polynomials here are characteristic polynomials of our system. And then they contain information about our critical modes and our eigenvalues of the system that contain information about frequency and damping, these two critical parameters. But there's one more thing that we need to do, and that's to determine the order of these polynomials. And there is a chapter in the thesis that deals with this problem. And there is no definite answer to this problem because it's a trade-off. If we decrease model order, then we cause increase bias in our estimate. But if we increase model order, then simply we are getting too many parameters to estimate, and that is getting more difficult also from the computational point of view, but also we are increasing variance of that estimate. So it should be some balance between these things. Also, there is another thing that we need to take care of is data length that we use for identification. If we use a really long data length, of course, then we can get a really good estimate. But the issue with power systems is during the time, the system can change. So we actually need also good time resolution that we follow how system changes in time. And in this chapter, you can find the analysis with these 4 methods for model order selection. To be honest, I don't think this chapter is a great theoretical contribution, but still I think it's very valuable because nobody has done this kind of analysis in the power system communities, especially not for this mode estimation and how to select the model order in an optimal way. So that's the general story I wanted to tell you how we essentially do this mode estimation and why it is important. The next thing is that what I want to tell you about is the optimal probing signal design. I already said what the probing is, and what we want to do, just to repeat it, is to estimate damping ratio of the critical mode of oscillation. That's our main objective. And I said that we disturb the system in order to accomplish that. But then there is a question. How should we disturb the system? Or how should the probing signal look like? And for that, in order to answer that question, there is one really nice formula, actually. I really think it's a magical formula that solves a lot of problems. Maybe it looks a bit scary if you see it for the first time, but actually it's not that difficult. What it says, it gives expression for the parameter covariance matrix of the estimate. Also, and the parameter covariance matrix is a measure of the uncertainty of our estimate. Of course, we want this uncertainty to be as low as possible. That's a good estimate. Since we have an expression for p theta is parameter covariance matrix and p theta inverse, of course, should be large in order to get a good estimate, and vice versa. If you analyze this formula, the only thing that we can actually influence here is this parameter, which is spectrum of the probing signal. So our accuracy depends on the spectrum of the disturbance that we inject in the system. And if we analyze this thing, if we just do ambient mode estimation and we don't have probing, which means that this spectrum is 0. And then we have only this constant part which describes accuracy that can be obtained by ambient-based mode estimation. And the second thing follow from this, if we have a really large disturbance as a probing, we can get arbitrary good mode estimate. So that's pretty much solve the problem. We just need to inject the disturbance as large as possible. Unfortunately, there is a limit in that. As I said at the beginning, the objective is to do this mode estimation in a non-intrusive way, which means that we are not really allowed to disturb the system a lot. So there is a certain limit how much we can disturb the system, but it should not violate stability limits. So obviously we have again a trade-off, and there are three things that we need to take into account here. First thing is of course control effort, which means the power of this disturbance that we're injecting in the system. Second thing is system disturbance, how big disturbance it will cause for the system. These two things are of course related, but they're not the same. Depending on where we inject our disturbance, it will have different effect on the system. So this system disturbance can be seen as a frequency deviation of the system, while this input power can be, for example, injected power as a disturbance. And that constitutes our objective function that we want to minimize. So these two things we want to minimize. Of course, we can get this objective criterion to be equal to 0 by simply not injecting anything. But of course, then we don't get the better accuracy. So we need to treat this accuracy as a constraint. So now we have an objective function, and we have our constraint. And this can be shown, this is a LMI, linear matrix inequality problem. And the solution of this is optimal spectrum of our probing signal. But that's only half of the story. If we have our optimal spectrum, we still need to disturb the system with some time waveform. And if we have a spectrum, there are infinite number of time domain signals that have exactly that spectrum. So now, actually that's a good thing, because now we can choose the signal, time domain signal, that the best corresponds to our wishes the most. And there are three methods actually how to do it, which are described in the thesis. But here I will just mention at least my favorite one, which I think is the most suitable for practical application. And this goes like this. So we have our spectrum as a result of our LMI problem. And that spectrum is described by autocorrelation coefficients. So autocorrelation coefficients describe our spectrum. And we also know that autocorrelation sequence can be estimated from the time domain signal in this way, using this formula. And our objective is, of course, to find this time domain signal, which will have autocorrelation sequence that is as close to as possible to this spectrum that we determined in advance. So that's optimization problem again that can be solved. And the dimension of this problem is, of course, number of samples in our probing signal U. Since we can have thousands of samples, that's quite complex optimization problem. But luckily, there is also a method to do it recursively, sample by sample. And practically we apply a method to conquer and divide and conquer, which makes this complex optimization problem much easier and solvable almost in real time. So, that's it. Here I want to show you some results, how spectrum looks like in a case of when we want to minimize disturbance that we are rejecting. We are applying this to a KTH node 32 test system, which has 2 critical modes, and we used reactive power injection as a disturbance. And we also defined accuracy that we want, which is damping ratio variance, which has to be smaller than some predefined value. And here, this is how spectrum looks like in case if we want to minimize disturbance in the system, which we define here as deviation of the voltage magnitude. What's important here are these numbers. First, as our reference, as a benchmark, we used white noise excitation. So it's white noise that will satisfy this criterion, this accuracy. And what can be shown by applying this optimal probing signal design, we can get 5 to 7 times. The same accuracy can be obtained by 5 to 7 times weaker excitation. Or to put it in another way, if we have the defined disturbance, power of the disturbance, we can get 4 to 5 times better accuracy simply by shaping the spectrum in an optimal way. Here, I can use the same equation that I really like to solve also other problems by using pretty much the same framework. And that problem is optimal signal selection for mode estimation. It can be shown that only several signals contain enough information to obtain a good mode estimate. If we use a larger number, of course, a larger number of signals, of course, it increases computational complexity of the problem, but also it creates bias. And that's a quite complex analysis, but we are definitely motivated to use as a smaller number of signals for our mode estimate. And what's important here, what is the hypothesis that we use, is that variance of the estimate is a good measure of estimation quality. And as I said, okay, in this case, we want to use it only for ambient-based estimation, which means that we don't have this part of equation, so we have this constant part. So what we can do is very simple. We just compute this variance for all the signals, we rank them according to this variance, and we select the top ones. And these are signals which will give us the smallest variance of our estimate, which means the better estimate. And here I want to show you the results, and I run it for voltage magnitude signals. I compute it for all the signals and for voltage angles. These are values of these variances that I computed, and here are locations of voltage magnitude and voltage angles. Because of different nature of the signals, actually location of this will differ. And here we are talking about mode, dominant path goes like this. So it depends on the type of the signal where this location is. So this is how I showed you this equation that actually can be solved to solve these two different problems: signal selection and optimal probing signal design. Okay. Did I lose you? Oh, okay, good. The next topic that I want to cover is what to do if we have a non-white noise loads. As I said, that's an generally. But actually, in reality, it can happen that we have loads that don't behave in that way. So we have non-white noise behavior, and sometimes we associate this behavior to force oscillations. And that's getting actually quite hot topic. And what's widely recognized, if we have this kind of force oscillations, that corrupts our mode estimate, simply because we have some input that we don't take into account in our mode estimation. So we wanted to address this problem. And the main idea behind was to monitor all these loads. So if we monitor them, then we can take into account if we observe that the load doesn't behave as expected. An idea was to monitor all the loads and use input-output identification. So it means we have a system, we monitor our inputs, we monitor our outputs, and we identify the system. Unfortunately, the issue with that, we cannot put PMU at each individual load, simply because there are millions and millions of these loads, so it's not possible to measure it. But what we can measure is a border point between transmission and distribution. And then we monitor equivalent load of some distribution area. So this is how it looks like. There is a load power and this border point, which is load power as an excitation to the transmission or the power taken from the transmission system. And we have, of course, our state variables that we, voltages and angles and so on, currents, power, that we monitor by PMUs. And then we can run this identification and to estimate this transmission system. The issue with this is that what we estimate is actually modes of only transmission part of the system. Which means that in this way, we neglect effect of loads. So what we actually run is a direct closed loop identification, because we have this closed loop here, which goes through loads, because power of flows depends on the voltages or on the state of the transmission grid. But good thing about this, and that was actually our first hypothesis, that these modes are predominantly determined by the transmission system, while distribution and loads have secondary effect. And that can be shown. And here, this graph actually shows what happens if we have a large range of load models, how these modes changes with load change, with parameters of the load when we change these parameters. And it can be shown that whatever we do with loads, literally whatever, the difference in modes will be less than 2%. Of course, 2% is quite small, but it's not, we cannot really neglect 2% error in our mode estimation. But still, what we thought, okay, we can solve one problem imposed by force oscillation. And for that, we have to pay a price in this inaccuracy of 2%. But actually, the situation is much better than that, because this 2% corresponds when we don't have any idea of our load models. But that's never really the case in reality. There are methods also how to identify load models, or we simply can assume based on heuristic. So this range of 2% can be significantly reduced. And if we, of course, if we assume these models, we can compensate our mode estimation results. And here I want to show you some results. Here we applied Walker method, like classical method for mode estimation. And of course, we also use a KTH in order to test system. We use Monte Carlo simulations to validate stochastic properties of the mode estimation. And what can we see here? That there is this force oscillation here that is estimated as a real system mode. And that's a false alarm that we want to avoid. And the thing is even worse, is that there is this real system mode that is not identified at all. So we didn't identify our real system and we have a false alarm. And that's a problem with classical mode estimators. With N4C method, situation is a bit better. At least we estimated the real mode correctly, but still force oscillation gives a false alarm. And if we use our method with input-output identification, we neglect this force oscillation. And we just estimate our real system modes. But just to be fair, we compared our method with classical methods in case where all the loads are white noise. And of course, then classical methods don't have any issue. And then we compare performances, and it can be shown that also our method behaves more or less in a similar way as the classical results, which means that we do not compromise mode estimation significantly with our method. And of course, we solved one huge problem that is imposed by forced oscillations. And here I want to show you prototype implementation. So up to now, I showed you mathematical background, how we address these different issues related to mode estimation. But of course, if you really want to make a product, it also has to be tested in a real life environment, which includes also communication network and all other things that can go wrong in a practical implementation. And luckily, thanks to Luigi, we have a quite nice lab here that is, it has all these components just like in a real system, like PMUs, communication network, PDC or phasor data concentrator, and one really important component called software development kit, which enables us easy access to these PMU data streams. And once we have these PMU data streams, I use the LabVIEW application. I have PMU data stream as a LabVIEW variable, and then I can play with that and develop any kind of user application. Also, we have a real-time simulator, so we can play with different disturbances and see how the different systems behave, but also we can use real-time measurements. And that's actually what I've done. Here you can see a graphic user interface of prototype of mode estimation application. I developed it, as I said, in a LabVIEW environment. And here you can see some results with the real life data. Actually, these are just voltage magnitude signals from our outlet. So it was quite cool because we can actually see what kind of modes we have in the Nordic system in our lab. And here are some modes that we identified: 0.39 hertz with the